Righto, this is a worked example for the normal distribution hypothesis test with the normal distribution, and it also illustrates the concept of the sampling distribution as well. So, what have we got? A machine fills paper bags with flour. Before maintenance on the machine, the weight of the flour in a bag could be modeled by a normal distribution with mean 1005 and standard deviation 2.1 both grams. Following this maintenance, the flour in each of a random sample of 8 bags was weighed. The weights in grams were as follows. We've got a list of numbers here. Carry out a test at a 10% significance level to decide whether the mean weight of flour in the bag filled by the machine has changed. Not necessarily it's greater or less than, just has it changed. Assume that the distribution of weights was still normal with standard deviation 2.1. Well, that's what we would do anyway. In any case. So what have we got here? So the random variable here, we're assuming that this random variable is actually normally distributed with a mean of 1005 and a variance of 2.1 of the standard deviation, 2.1 squared with a standard deviation of 2.1. Okay, so some thoughts here. We've got a random sample of 8 bags. So when we take the mean of these, this is the ordinary thing, the natural thing that we would do with the normal distribution is take a number of readings, take the mean of them. But once we've taken the mean of them, we have effectively generated a new random variable, and this random variable has got a distribution which is based on this distribution, which is the distribution for a single measurement. But now we have something slightly different, and it's got the same mean, but it's got a different standard deviation. Now we call this this new random variable large X bar. It's got a normal distribution of 1005 and a variance of 2.1 squared divided by 8, which is the sample size. So it's actually got a smaller variance and standard deviation. Just another thing on this, this is a relatively small sample. We'll go back to the video on sampling distribution. You know, if we've got a larger sample here, it doesn't really matter what the original distribution is, whether it's normal or uniform or anything else. If your sample is large enough, and therefore you're dividing by a big enough number here, let's say, then the sampling distribution, the distribution of this generated random variable, will tend to normal. It will approximate to normal. In this case, 8 not really big enough. So I think it's important that we know that if we have a small sample size, that we're actually starting with a normal distribution, because if we're not, then effectively the X bar probably won't be normally distributed. But anyway, here we know that we're dealing with normal distribution. We've got a sample size of 8, so we're making a decent assumption here that this sampling distribution is normally distributed. Now, the actual sample that we've got here has got a mean of this figure here, 1006.2875. So that's what we've got there. So what are we doing? Carry out a test at the 10% significance level to determine whether the weight has the mean weight of flour has changed. These are grams, they're actually masses, of course. So how do we go about this? Right, so first of all, we're going to form our hypotheses. The null hypothesis is that the mean is still 1005, and the alternative is that it's changed. So in other words, that it's not 1005. We're doing a two-tail test, simply because we're testing that it's changed. So the thing we kind of difficult to sometimes get your brain around with these questions is that what we would normally do is we form our hypothesis and then we take the data. Of course, when it's expressed in a question like this, we can actually see the data anyway, can't we? But if we'd imagine that we haven't taken any data, we just wanted to know whether or not the mean weight or the weight had changed, then you know, this is what we would formulate. So we're doing a two-tail test at 10%. So if this is our sampling distribution here, here's a middle of this will be 1005, and these are our tails. So these will be our critical regions. So what we want to do is find the probability that we've got a value as extreme as this 1006.2875, and if it fits in, if such a value actually falls into one of these tails, probability of it means that it actually its value is here, so its probability is less than 5%, or here, so it's less than this area. Then we would conclude that that's basically something that's arisen not just by random chance, that it's actually quite an extreme result and is giving us a doubt as to our original null hypothesis. So, okay, so we can just do this. I mean, if we translate this, that's going to give us a standard deviation of 0.742. So the sampling distribution's got a mean of 1005 and a standard deviation of 0.742, and we want to test whether or not an extreme value, or a value as extreme as this, falls into one of our critical regions. Well, this probability, we can just pop this into our calculator with the normal cumulative. So we're looking at a lower of 1006.2875, anything up to anywhere up the right, so some large value, 4 nines, 5 nines maybe, into the calculator, these parameters, and that's going to give us a probability of 0.0413, whatever. Now that value is less than the probability of this tail here. So therefore, the test statistic is going to fall inside this critical region. This value is less than the alpha value, so the test statistic falls inside the critical region, and therefore we're going to reject the null hypothesis because we're concluding that this sample mean here is more than we would reasonably expect as arisen from random variation. Okay, so we've concluded that the mean weight has changed. What the mean weight actually is now, of course, is a matter for a separate study. We have merely concluded that it's not the original 1005, that we need to consider something different. Okay, so that is hypothesis test with the normal distribution, and we also talked about the sampling distribution with reference to the central limit theorem. So hopefully it's been useful, and see you next time.